Hello and welcome to our paper, Self-supervised monocular depth estimation. Let's talk about the weather. Use a self-supervised approach with a monocular camera to estimate per pixel depth in a scene. Previous approaches, like monodepth 2, excelled at estimating depth on clear scenes as they were explicitly trained in clear, sunny environments. Although these methods struggled with changing domains. For example, we show that monodepth 2 struggled with rain, fog, and nighttime domains. We will first demonstrate how monodepth 2 learns accurate depth on clear scenes. We start with 3 consecutive images and define the depth and pose networks. We then input our target image into the depth network to produce a depth estimation. Furthermore, we input 2 consecutive frames, the previous frame and the target frame, into the pose network to give our pose estimation. We do the same process for the target frame and succeeding frame to find eagle motion between 2 frames. Here we define inverse warping as displayed. We use the depth and pose estimations to create reprojections of the target image from the previous frame and the succeeding frame. We self-supervise the pose and depth as we compare the reprojected target images with the real target image, using photometric loss as shown. Finally, we optimize for these reprojections using a minimization which finds the best per pixel match between reconstructions. When using the baseline method to train on augmented data, we see catastrophic forgetting. We show monodepth 2 train with augmented data and train with the original dataset. The depth network trained with augmented data is more robust to different augmentations but struggles with the original sunny data. We now move over to an implementation of robust depth, which avoids catastrophic forgetting and leads to outstanding robustness when compared to the baseline method trained with augmented data. We take the same unaugmented images and introduce an augmented pair. Once again, we estimate the depth for the unaugmented target image, but now we estimate the depth for the augmented target image. Furthermore, we estimate the pose for the unaugmented and the augmented images between the target frame and the previous frame, and the target frame and the succeeding frame. Following monodepth 2, we create reprojections of the unaugmented target frame using the unaugmented depth and pose estimations. However, we cannot naively create reprojections of the augmented images using the augmented depth and pose estimations, as these images suffer from inconsistencies between frames. To exploit the consistency between unaugmented images and the better unaugmented pose estimation, we use semi-augmented warping. As you can see, we still have the depth estimation of the unaugmented and augmented images. Using these 2 estimations, we introduce pseudo-supervised depth loss, where the unaugmented depth supervises the augmented depth and vice versa. Notice that the only difference between the semi-augmented and unaugmented reprojection is the use of augmented depth. Therefore, we can create a mask that has pixels in which the unaugmented depth leads to a better reprojection than the augmented depth. The mu in this case is auto-masking from monodepth 2. We also create a mask in which the augmented depth leads to a better reprojection than the unaugmented depth. From here, we can find our loss in 2 directions, where the underlined symbols represent the gradients being cut off during backpropagation. Following this same scheme, we demonstrate our one-directional pseudo-supervised pose loss, which uses the unaugmented pose estimation to supervise the augmented pose estimation. We break down the pose into its rotation and translation components and simply find the L1 loss between them. From here, we can find the photometric loss between the target image and the reprojected images. We have a final per pixel photometric loss function as shown. We optimize for both the unaugmented and the augmented images to avoid any catastrophic forgetting. It is vitally important that these self-supervised monocular methods are capable of operating in year-round conditions. In this demonstration, we can see all the various augmentations used. We show different forms of image degradation, shifting time of day, and a variety of weather conditions. We see that monodepth 2 is largely outperformed by robust depth in all augmentations. Furthermore, to demonstrate that our method is agnostic to depth backbones, we train with Monovip's transformer-based depth network. When using Monovip's backbone, we see that our model still significantly outperforms state-of-the-art depth networks across domains. Furthermore, we introduce our augmentations named vertical cropping and tiling, which both aim to remove the depth network's dependence on pixel position when estimating depth. For self-driving vehicles, sensors such as LiDAR struggle in some of these domains like rainy and foggy scenes. The ability to use a single camera to estimate depth in a variety of domains has strong advantages when other sensors fail. Finally, we show qualitative results on out-of-distribution data, which demonstrates impressive performance in multiple domains. Focusing on the foggy cityscape dataset, we can see clear distinction of better performance when comparing the depth estimations of monodepth 2 and robust depth. Furthermore, when using monovit's backbone, we see even finer improvements around the edges of vehicles and posts. Moreover, we test our model on the challenging nighttime domain from our new scenes. We again show a more robust depth estimation from our model compared to the baseline models. Further demonstrations show that our method is agnostic to the depth network's architecture by using monovit's backbone. Penultimately, we use the driving stereo dataset to demonstrate our performance on foggy and rainy data, again showing impressive performance improvements. The same pattern is shown for more complicated depth networks. We have shown that robust depth is able to cross-generalize to multiple domains whilst avoiding catastrophic forgetting. Here we show our quantitative results on the outer distribution data. We can see that robust depth outperforms or matches the performance of the current state of the art. The paper contains more details as well as a meticulous ablation study of all the components of our algorithm. In conclusion, we achieve this using semi-augmented warping and novel pseudo-supervised loss scheme and optimizing for both augmented and unaugmented image pairs.